First,
Yeah.
good evening, everyone. It's a great pleasure to have Professor Subir Sarkar from Oxford with us once again. I think Subir is very well known to all of us, so no formal introductions today, except to note that I think it's very interesting that the cosmic dipole anomaly observation and analysis that Subir and group have been doing for a few years now, to my understanding, is moving mainstream and being taken very seriously. And now in today's talk, Subir is addressing another question. Is the claimed acceleration of the universe really there? So great. Over to you, Subir.
Thank you so much. And thanks for inviting me, both Michael and Tejinder. Uh, so, this talk is going to be largely about cosmological data and techniques for analysis. It's not really going to be about the fundamental questions that people who are attending and yourself in particular are interested in. But it is of great significance, the outcome of our discussion for those fundamental questions, in particular for the question whether the universe is in fact accelerating, dominated by dark energy, which is vacuum energy driving the acceleration. So I've already announced my abstract. So this is essentially what I'm going to talk about: observations rather than the theoretical mechanism or mechanisms that might explain them. So I shall focus on what we can actually see on the sky, and hope to arouse your interest in thinking of possible explanations. Now, this discovery is, of course, very well known. It has won every prize that is going. And I have put a question mark in the title, however, after the statement is the universe accelerating. And that's because I wish to appeal to Ian Hinchcliffe's rule. Ian Hinchcliffe is a well-known particle physicist at Berkeley, and he was, in fact, did his DPhil here at Oxford. And this rule is, if the title of a scholarly article is yes, no question, then the answer is no. Now, one of you might be thinking, isn't that Betancourt's rule, which Betancourt was the newspaper editor? And that's a different rule then, that things are usually named after somebody who was not the originator, but that's not what I'm talking about here. Of course, these rules also should be taken with a pinch of salt because they're not logically consistent. I mean, is Hinchcliffe's rule true? And according to this mathematician in Paris, it's false, but only if it is true. So there you are. Now, let's go straight to the observations that have led us to this point where we believe that the universe is accelerating. And this is going back to the late 1990s, you will recall, when two groups, uh, said to be independent, although they did have a key member in common, said that when they looked at how bright distant supernovae were, and plotted the magnitudes, that is the measure of the brightness, versus the redshift, which you get from their spectra, and that's a measure of the distance, then you see that the data do not follow what would be expect for a universe. This blue line here, second from the bottom, which is dominated by matter and is therefore decelerating. Instead, the data systematically lie above it and are consistent with a universe where the expansion rate is actually getting faster, below about redshift of 1. Uh, the quantitative observation was that, I'm quoting from the paper here, that high redshift supernovae are about 15% fainter than the low redshift supernovae. This is the actual measurement. So you can get a sense of the precision required to make this statement. And all this was based on of order 50 supernovae, uh, between the two collaborations together. They added up to around 100, somewhere in common between them. Now, that was quite some time ago, and we should first ask, how did they come to that conclusion? So the analysis framework they employed is the standard cosmological model. So here is a computer simulation of structure formation in the standard cosmological model. The key thing about this figure being that although there is a great deal of structure in it, it is still statistically isotropic and homogeneous, and because that's an assumption of the model, the Robertson-Walker metric, which I have written here in using conformal time, eta, rather than time, t, in order to make it look like a Minkowski metric, which of course it is not. It's not Minkowski even at infinity. And now, in order to do cosmology, you need dynamics, and that is provided by Einstein's theory of relativity. And of course, all these efforts in cosmology began shortly afterwards, with the first paper by Alexander Friedmann in 1922, so over a century ago. And this universe that was constructed was populated with ideal fluids, which have a diagonal energy momentum tensor. And using this metric, as you all know, you can construct the Riemann tensor, you can construct the Ricci tensor, the Ricci scalar, and you can relate these geometrical quantities to the energy momentum tensor on the right-hand side via Newton's constant. And this is, of course, rather complicated. There are 10 coupled equations. And moreover, a little later, it was realized that T mu nu, which was taken to be just the energy density of non-relativistic dust, of collisionless, pressureless particles, uh, actually, if we consider what particles are, namely excitations of quantum fields, then one ought to also take into account the zero-point energy of those fields. And that also behaves as a cosmological constant, which is necessary on the left-hand side by virtue of the local coordinate invariance of general relativity. And therefore, you have this capital lambda, which is this lambda that is the coefficient of the metric on the left-hand side, plus the contribution from the fields, the quantum fields in the universe. And these two add up to give you a quantity lambda, which then enters the simple single Friedmann-Lemaitre equation that results from these complicated 10 coupled equations by virtue of the simplification afforded by the Robertson-Walker metric, maximally symmetric metric. And as you all know, I can rewrite this equation by dividing through by the Hubble parameter square and defining these fractional energy densities in the matter, in curvature of spatial sections, and in the cosmological constant. And then I have a very simple expression of the whole shebang, which is this omega matter plus omega curvature plus omega lambda equals 1. There are no more terms because of the assumption of isotropy and homogeneity and ideal fluids. There could be in principle be many more. But this is what we work with, and this has not changed since 1922. There is, of course, a second equation, what actually is the Raychaudhuri equation in vastly simplified form, which tells you how the second derivative of the scale factor reacts to the energy content, which is not just the energy density rho, but has this plus 3 times the pressure added, because pressure is also kinetic energy, it gravitates. And since we notice here that the pressure is the negative of the energy density for the vacuum, in principle, it could be negative and overcome this quantity, this number here, and therefore reverse the sign and make A double dot positive. And therefore, it was, I think, but the structure of this construct, not unexpected, that subsequently, when data improved and one could measure the Hubble diagram out to a redshift beyond 1, that it was concluded that there was evidence for negative pressure accelerating the universe, as we saw in the past slide. And what that tells you is that this quantity, 0.8 times omega matter minus 0.6 times omega lambda, is a negative number. That comes from the supernovae. Type 1 is supernovae, of which more later. There is also evidence from the cosmic microwave background, which exhibits these fluctuations mainly on 1 degree scales, because 1 degree is the horizon at last scattering surface. And that, when you take a power spectrum of it, reveals itself as this huge peak at about multiple of 200. These are actually sound waves in the primordial plasma, which were frozen at the point where the plasma turned neutral very quickly. And this is the horizon and the last scattering surface. Anything you see on the left-hand side on larger angular scales is something that has to be an initial condition. It can't have been due to any causal influence within our light cone. And this, of course, where these fluctuations came from is another story. We won't go into that here. But these observations have been increasingly precisely made. And what we know from the position of this peak is that the curvature is very close to zero. We measured the curvature modulo the overall scale, distance scale, which is set by the present-day Hubble parameter. And the heights of these peaks measure other things. So, for example, the height of this to the bottom of this trough, that measures the baryon density because the baryons load these oscillations. And the relative heights of the peaks measure the matter density and so on. But you don't measure lambda here. Nor do you measure lambda when you look at the same oscillations imprinted on the baryons, which then later fall into galaxies. Of course, most of the matter is meant to be dark matter, but the galaxies have the baryons lighting up what we see on the sky. And they show these very faint remnants of these oscillations, only about a 1% effect here. And this has been teased out of the data very nicely by, most recently by the DAISY instrument on the Kitt Peak telescope. And they tell us that omega matter is 0.3. So putting all this together, we have that omega lambda is 1 minus omega matter minus omega curvature, so that's 0.7. And since omega lambda is defined as lambda over 3 h naught square, that means that lambda is 2 times h naught square. Now, this is not normally highlighted. What is highlighted is plots like this, where you show omega lambda versus omega matter and how these three observables nicely intersect and give you the standard cosmological model, the so-called concordance model. And I want to make the comment that the fact that lambda turns out to be something to do with the present day expansion rate is kind of baked into this model. But that is what makes me immediately suspicious of the value, because it can't really have any other value. H naught is the only dimensionful parameter in this model because of the assumed isotropy and homogeneity and the ideal fluids, as I've said before. Now, in energy units, H naught is a infrared scale. It's the size of the universe, 10 to the 28 centimeters. And the inverse of that in energy units is some tiny scale like 10 to the minus 42 GeV. But Gn is extremely weak. Its gravity is weak because the corresponding energy scale is huge. It's 10 to the 19 GeV, the Planck scale. So if I take the geometric mean of these two, which is what is being done here when I construct the energy density for lambda by writing it out in Planck units, so it's h naught squared times Planck mass square, and therefore it is 10 to the minus 12 GeV to the power 4. That's the energy density. But I want to emphasize that nobody has so far seen this energy density on the sky. We have inferred lambda from geometric probes like the luminosity distance of supernovae or the angular diameter distance for baryon acoustic oscillations and so on. We have not actually measured a dynamical effect of lambda, which should be its negative pressure. And this is particularly important because a lot of people seem to think that the cosmic microwave background has established this model beyond doubt, and in particular measured lambda. And indeed, the data is very well fitted by this 6-parameter lambda CDM model. But actually, lambda was not even relevant at the time of the last scattering, because that was a redshift of over 1,000. So the matter density was 1,000 cube times larger than today, but lambda was the same. So it was 10 to the 9 times smaller. It was completely unimportant. And much of this structure is really because the primordial fluctuations are of a particular kind, the adiabatic scale invariant fluctuations are very close to scale invariant, and they would leave you this imprint regardless of whether lambda is in the picture or not. But it's going to take me too long to convince you of this by going into the mechanics of how this pattern develops. So let me just show you this table from the Planck paper, which shows all the parameters they extracted from the posterior after doing a Markov chain Monte Carlo scan fit to this data. And you see all these parameters with lots of decimal points, etc. But I just want to make the point that you will not find any entry for lambda here because they don't measure lambda. They infer omega lambda by subtracting omega matter and omega curvature, which they do measure from 1. You can ask any your favorite CMB expert, he will confirm that, or he or she will confirm that. And it is true that in principle, the CMB can be a probe of lambda. There will be a subtle correlation between the CMB and foreground structures. After lambda comes to dominate, because it has got negative pressure, it will make potential wells shallower. And that causes a lack of cancellation between red shifts and blue shifts for the CMB photons that are passing through the structure as it is evolving. But that effect is tiny. It's less than 1 microkelvin. So this is around 80 microkelvin RMS. So it's a tiny effect, and that would need at least 10 million galaxies to be measured precisely between 0 and 1, and this correlation sought. Now, that might happen. The data is very soon coming, but it has not been done yet. So why am I talking about acceleration now? All this is supposed to be well established. It's in textbooks. There are three issues which are important. So the first is the statistical analysis of the data. Now, I'm prepared to bet that most of the people who are on this talk are not aware that when people analyze the supernova data, what they do is that they take the measured magnitude, this mu, for the ith object, and they subtract from it they subtract the observed magnitude from the model value, which is basically the one in the standard lambda CDM model, and you square it and you divide it by the square of the uncertainties. Now, this is perfectly kosher, and that is what gives you a chi-square. But they do something more. They add an error bar to each data point, this sigma int here, and they adjust its size until you get a good fit to the data, until you get a chi-square per degree of freedom of unity, perfect fit to the data. And this is actually unprincipled. It is fine for determining model parameters if you are convinced that that is the right model. But it is not good for model selection for obvious reasons. You are clearly biasing yourself towards the assumed model. And the way to get around this, which was actually presented nearly a century ago by Fisher, is the maximum likelihood estimated. It was considered to be the greatest statistical advance of the last century. Even though I have to say that the proponents of this so-called adjusted chi-square method called our maximum likelihood estimator unorthodox statistics. I'm not sure what is unorthodox about it. It's the standard tool, industry standard. And it has indeed been adopted after we introduced it. And also in the Bayesian context, we did a frequentist analysis, but you can do it in the Bayesian context, and there it would be called a Bayesian hierarchical model. The second advance since those initial years is that many more supernovae are now available. So we did our first analysis with the joint light curve analysis catalog, which was of 740 supernovae. But more recently, about the number has doubled and perhaps even tripled more recently. And so that means one can ask some questions now that we couldn't earlier. But even more importantly, as was mentioned at the start of this talk, there have been recent challenges to the very fundamental basis of the cosmological model that is being used to analyze the data. That is to say, the assumption of homogeneity and isotropy on large scales, which is dignified by the cosmological principle. And I shall briefly show you why we believe that this does not actually hold for our real universe, because there is a mismatch between the asymmetries we see because of our special position in the universe, in the microwave background and in the matter. The fact that we are in a asymmetric position is by itself not unusual. The Hubble flow, etc., only happens on large scales, not on small scales, where you have so-called peculiar velocities. But these dipoles in the matter and in radiation should match, but they don't. And there is, in fact, it turns out that we are this peculiar velocity that we have, in fact, is part of a coherent flow in the local universe that is stretching out much further than you would expect in this lambda CDM model. Now, this brings me to the only bit of theory that I want to talk about here, which is due to Christos Sagas, a radiologist at Thessaloniki. And he's been saying for quite a number of years that if we are indeed not ideal observers, as is usually, there is a concept of a co-moving observer in cosmology, but in fact, if we are an observer who is embedded in a bulk flow that carries energy momentum, then as it says in his paper, that such an observer might find that the acceleration is actually anisotropic. And this should be, in fact, something that is observationally detectable. So having heard Christos give a talk about this quite early on, I think it was back in 2011, I put it to him that one could look for this anisotropy using real data, which he encouraged me to do. And I'll just show you how this happens. If we happen to be in a flow, then depending on the sign of whether the flow is converging or diverging, you would have an additional term for the deceleration parameter, which can cancel the usual term. And if this flow is in fact converging, which our local flow appears to be, then even if globally the universe is decelerating so that Q naught is positive, that's how it's defined, we might measure it to be negative. And a surefire signature of this is that it would be anisotropic and mainly towards the flow direction, which is roughly the direction of the CMB dipole. So this was the sort of suggestion made from theory, and then the question is, what do the observations say? And that is what we undertook later. And this was something that we first did in 2019, and it was published as a editor's choice letter in Astronomy and Astrophysics. And in fact, we showed quite clearly not very high significance, but certainly at 3.9 sigma, which was not still 5, because the number of supernovae was rather small, that there was an anisotropy directed towards the microwave background hotspot. I'll show you the data in a minute. And we highlighted that this could be an artifact of our being non-Copernican observers rather than evidence for dark energy. Now, as you can imagine, this got a huge lot of pushback. And in fact, it was led by Rubin and Heitloof. I'll discuss their objection in detail later, and others. And we have more recently managed to counter those objections by analyzing a bigger data set called Pantheon Plus, which in fact now shows this anisotropy at more than 5 standard deviations. Now, the outline of this talk, therefore, is that I shall first tell you what is supernova cosmology. I'm assuming absolutely no knowledge of anyone, although I can see there are some experts in the audience, but allow me to go back to the basics. And then I shall tell you why we believe the maximum likelihood estimator is a more principled analysis than this adjusted chi-square. I'll briefly tell you about this Collin et al. 2019 paper because that leads to the more recent analysis we have done. It's the same thing, just done with more data. And I'll tell you a bit more about the supernovae standardization because that is absolutely key to what is done with supernovae. And in fact, my concerns about these issues are actually shared, I know, by many cosmologists. And they, however, say, well, in that case, we can, look at something cleaner like the cosmic microwave background. But as I've just commented, the cosmic microwave background does not provide any model independent confirmation of, evidence for lambda. I'll also talk about something particularly egregious, which are called peculiar velocity corrections. Now, this I'm afraid will get a little technical, but I really think I ought to highlight it because my uh, collaborator Ramiz is particularly keen that this should be made known to a wider audience, that people should be aware how the supernova data are manipulated in order to give a certain result and what are the assumptions that underlie it. So I'll end with our recent paper where we show that not only is the cosmic acceleration anisotropic, the little isotropic component that was always there, which in principle could be attributed to lambda, actually becomes deceleration when you apply a recently proposed correction to the supernova magnitudes correlated with their progenitors, with the stars that went bang. This is not our work. This is the work of actually two groups of Korean astronomers who have been looking at it for quite some time. And this has been opposed by other astronomers who are pro acceleration. I'm not an astronomer. I will not presume to, you know, give an opinion about the matter. I shall simply show you what is being said and what the data actually show, and you can make up your own mind. Okay, so I have half an hour to get through the rest of the talk, but fortunately, I think there is an hour for questions afterwards. So hopefully, I can go through reasonably quickly and address your questions later. So what are type 1a supernovae? They are basically supernovae that are thermonuclear explosions believed to involve a white dwarf star. People often say Chandrasekhar mass, 1.4 solar masses, because that seems to suggest that it's some kind of a, you know, determined by fundamental physics, but actually the masses do vary. They're not always 1.4 solar masses. There's a lot of variation amongst type 1a supernovae. If I've asked my local, astronomers, supernova experts, they tell me they don't even know exactly what mechanism it is. It could be one of several. But what is clear is that thanks to advances, major advances that were made in the 1990s in building cameras with charge coupled devices, CCD cameras that can scan the sky repeatedly every night, you can measure the light curves of the supernovae where they go to a maximum and then fade over days. And this tail that you see at the end, that is actually the radioactive decay of nickel 56, which is being synthesized in these objects. But you can't simulate them. They are, they're a star as big as our sun that goes bang, and the deflagration front that propagates out, I'm told, is about this thin. And so you can imagine there is a certain challenge involved in trying to simulate something like that in an object the size of our sun. But what we do know empirically, thanks to Phillips, an astronomer at the Anglo-Australian telescope some years ago, is that because you now know the widths of the light curves, because you have seen the rising part of the light curve. So normally this part of the light curve would not have been seen in old, previous years, because you only see something when it appears on the sky. But now, thanks to these CCD cameras, you can go back and look at that patch of sky 2 weeks earlier, and you can get these measurements which are on the rising part of the light curve. And therefore, you can measure the width of the light curve. There is a convention as to how you measure that. But when you plot one versus the other, you see a correlation. And the correlation has got slightly different slope according to whether you're measuring in the blue band or the infrared band and so on. So these are all astronomical jargon. But look at what it does to your data. You normally have a huge scatter in the supernovae. This is the magnitude plotted versus the days since maximum. And you can see that the scatter is almost an order of magnitude. This is the log scale. So it's nearly a factor of 10 in the absolute, in the brightness that you see. But when you make this correction, when you stretch the color curves out and do so according to the color band in which they're measured, then you see they all fall on more or less the same curve, and you have reduced the scatter, which was like 0.8 magnitudes, down to about 0.15 magnitude. And this was this many astronomers have been involved in this, not just the ones who were awarded the Nobel Prize. Hamui is an astronomer who was working in Chile, for example. And because of these empirical corrections that were done by various astronomers, supernovae became it became possible to use them to do cosmology. However, different surveys were using different ways to reduce the data, and it was not until 2014 that we had the first public catalog available in which the data from different surveys had all been analyzed using the same so-called template, light curve template. So these are catalogs of, for example, these green ones are the supernova legacy survey, which was done only in 4 directions in the sky, these little green spots that you see, this one here and this one here. The red ones are the local supernovae, which are, as you see, within a redshift of 0.1 or so, and they're all over the sky. And then you have very distant supernovae beyond redshift of 1. Now, these can only be seen from the Hubble Space Telescope, the purple ones, which are also randomly over the sky, but there are only about a dozen of them. Most of them are from something called the Good Survey on the Hubble Space Telescope. And then there was this gap in the redshifts in between, zero point 0.1 and 0.3 or so. And that was then bridged by the Sloan Digital Sky Survey, which is this imprint on the sky. So this is the state of the data. It's not as much or as uniform over the sky as one would like, but this is the result of many, many years of work by many, many astronomers. And this is why we can start asking big questions about the universe. So what is done is to take these observations of the magnitude and correct them, assuming that there is some absolute magnitude which is the same for all supernovae, and this the observed one, which is the one that has got a star on it. The star means you measure the magnitude at peak. You correct that for this stretch and color, and the coefficients of these are then tabulated. And this is from a tabulation of 740. I'm just showing you the first 2 entries. And the B stands for the B band. So now I'm kind of demystifying the jargon that is used in this field. Now notice that the measured redshifts are actually been already boosted to something called the CMB frame. And I'll tell you what that is. I should also mention that this need not be the end of it. After all, you are correcting for the stretch and the color. Might there be other correlations? For example, with the mass of the host galaxy, or the position of the supernova, how far is it from the center of the galaxy, the metallicity of the host population. You could think of anything. This is not theoretical. This is all empirical. So we have to let the data decide and use principled statistical measures to determine whether some parameter is relevant or not. But first, let me remind you what this CMB frame is. We know that the universe is not isotropic as is assumed in the standard Friedmann-Lemaitre-Robertson-Walker model, because we are not co-moving observers. We have a peculiar motion because we are being pulled by Andromeda. We are part of the Virgo cluster, which is moving in some direction. And all this results in a peculiar velocity of a few hundred kilometers per second. And Dennis Sharma, who introduced me to cosmology, actually predicted that there should therefore be a dipole anisotropy in the microwave background that had just been discovered. And indeed, it was discovered soon afterwards. The fact that this pattern follows just from special relativity and the temperature should vary over the sky according to the angle theta from this direction in which you are moving was actually first calculated correctly by Jim Peebles and David Wilkinson. And since this velocity, this temperature change is about 1 part in 1,000, beta is also 1 part in 1,000. It's in fact, to be precise, 369.8 kilometers per second. This is with respect to the frame in which the CMB is truly isotropic, or so we believe. So the idea is that if we boost ourselves in that direction at that velocity, then we should, this dipole should go away. And we'll only then see these little fluctuations of 1 part in 100,000 that we saw earlier. And that frame is important because that is we think, the cosmic rest frame. That is the one in which the Friedmann-Lemaitre equations hold. Now, why are we moving? Well, because there is inhomogeneity locally. We are not in an ideal homogeneous universe structure has formed. But it is believed that this structure should be smoothed out. If you average over scales exceeding a couple of hundred megaparsecs, then we should get to this CMB frame. Now, in anticipation of that, all data is routinely corrected by first transforming to the CMB frame, as the supernova data I just showed you, right? Is that a valid procedure? Well, first let's look at our motion a little more carefully. This is from George Smoot's Nobel Prize, Nobel Award lecture. Half of his prize was for this dipole anisotropy. Now, of course, he's talking about measurements from the Kobe satellite, which is orbiting the Earth. You might make the observations from a telescope on Earth. But whatever it is, you have to allow for the fact that the Earth is going around the Sun at 30 kilometers a second and reduce it to the heliocentric frame, which, of course, is dominated by the Sun. And that is the frame in which we will, in fact, talk about most of our data. That is the one that the observations are reduced to. But the sun and the solar system is actually orbiting around the galaxy in roughly the opposite direction to the microwave background hotspot. And that means that our real velocity of the galaxy is in fact twice that. It's much more than 369.8. It's closer to 620 kilometers a second. Because in fact, we are orbiting Andromeda, and we are orbiting, and we are moving coherently, the local group, towards something that used to be called the Great Attractor, beyond this supercluster, which is the neighboring one. And people have been looking for this great attractor because by the time we kind of map out to it or average over it, we should be, converging to the CMB frame. This, you know, not hypothetical. The CMB frame is a well-defined concept, but whether we reach it or not is the question. But in fact, we could have another frame. We could consider the local groove frame because we are, after all, embedded in this local bulk flow. And this is, in my view, the closest to this notion of the tilted observer that Sagas was talking about. But people also have this Hubble diagram frame, which is not only you boost to the CMB frame, but you also correct the sources, the supernovae, for example, they're in host galaxies, and they also have peculiar velocities. They are not necessarily in the Hubble flow. And you correct for them the peculiar velocities, and the total package is then called the Hubble diagram frame. And in fact, this is where, this is the cosmic rest frame. This is where you would expect the Hubble diagram to be isotropic and homogeneous. So you can see this proliferation of frames. And I would say that normally, when theoretical physicists or relativists talk about co-moving observer, they would really ought to kind of make a distinction between these frames because these are the kind of frames that observers know. Observers are measuring in the heliocentric frame. They have no idea, they do not know without being told how to do the transformation what any other frame is. But all these frames are related by simple Lorentz transformations, Lorentz boosts, they're local physics, special relativity, not a big deal. We know how to do all this. Now, what about a local universe? Now, this is actually extremely inhomogeneous, and this is how it looks like when it is mapped out by careful surveys. This is from the Cosmic Flows 3 survey that was led by Brent Tully and collaborators. And what these fine lines are showing you are the local flows, and the peculiar velocity is defined as the velocity that you normally have been attributed according to your redshift. You subtract from it the Hubble parameter times the distance. So this should be zero if you're in the Hubble flow, but in fact it is not. Out to at least a few hundred megaparsecs, we see peculiar velocities. And it is understanding these peculiar velocities that is important because corrections have to be made for this. And that is usually done, I have to tell you, assuming the lambda CDM model, which is the very model that you're supposed to be testing. If you look out further to a few hundred megaparsecs, 600 or 700 megaparsecs, this is from the Sloan Digital Sky Survey there is now a even nicer plot from the dark energy spectroscopic instrument, DAISY. Then you see this so-called cosmic web of galaxies, superclusters, clusters, etc., which is largely reflects what you would see in a computer simulation. That's what gave us confidence in this lambda CDM model. But you need to test whether this picture is correct, because the expectation is that if you are actually flowing towards this great attractor, which was thought to be the Shapley supercluster, and then our peculiar velocity should fall off as we average out over larger and larger scales. And we should converge to this cosmic microwave background frame in which we can then make further corrections for peculiar velocities and apply the the Friedmann-Lemaitre equations, right? This is the standard procedure. Is that actually supported by the investigations made to check the basis of this procedure? Well, here is a plot of the local bulk flow velocity as a function of the averaging scale. And there are technical issues to do with whether you use a Gaussian filter or a top hat filter and so on. I won't go into all that. What you see here is the expectation of the lambda CDM model, the purple line, and the 1 and 2 sigma uncertainties on that from cosmic variance, really. And the data, start for over 10 years. These observations are very hard to make, by the way, because you can't use the redshift as a measure of these distances. So you have to have independent measures of distance, and that's very hard to do in cosmology. They're very uncertain, Tully-Fisher or fundamental plane and so on, for respectively spiral and elliptical galaxies. They're uncertain by at least 15-20%. However, it is clear that the data at small scales is consistent with the expectation, but there seems to be something going on as you go to larger and larger scales. In fact, we raised the alarm with analysis in 2011. This is Collin et al. 2011, where we looked at type 1a supernovae, the subject of this talk, and found that although the uncertainty was very large, there seemed to be a higher velocity at a scale of 180 H inverse megaparsec than you would expect. Then Sloan Regional Sky Survey came in with the observation that kind of confirmed what we had found, and their error bars were smaller. And more recently, the Cosmic Flows 4 survey has found a clear discrepancy with the expectation going out to about 200 over little h. So little h is 0.7, and all scales in distance have modulo this h. That is because we are talking about co-moving distances. And this is important to emphasize that according to these observations, the bulk flow, as is say from this paper, is unlikely in the standard lambda CDM model at about 10 to, that's about 4.6 sigma or something like that. It's still not quite 5 sigma. And as I said, there's a lot of discussion about whether these distance estimates are reliable and so on. But I think this is an area to watch. But it was not by itself convincing. So we looked out further in redshift, and we made this measurement of whether our local velocity is indeed the entire explanation for the dipole in the cosmic microwave background, whether it's truly kinematic in origin, by doing something that George Ellis and John Baldwin had proposed back in '84, which is that you look at the similar dipole that should arise in distant sources at high redshift. And I've given a talk about this before, so I'll just remind you that what we did, this was with Nathan Sekres, Mohammad Ramiz, Sebastian von Hauseger, Roya Mohai, and Jacques Collin. We looked at a catalog of 1.4 million, actually later 1.6 million quasars whose redshift distribution for a subsample of which is shown here, measured by the EBOS survey using Sloan. And you see here the median redshift is higher than 1. And in particular, 99% of them are beyond redshift of 0.1. Redshift of 0.1 is 300 over little h megaparsec. So that is supposed to be far enough out that you should be in the Hubble flow. Now, when we smooth this map and measured the dipole. That dipole turns out to be different from what we expect. Now, what we expect we can determine from the flux distribution and the spectral index distribution of these quasars according to the Ellis-Baldwin special relativity formula. And what you see is that the dipole that we measure in the quasars is significantly above what you would expect on the basis of special relativity, which is this hill that you see here. And that has taken into account all the uncertainties in the flux distribution and the spectral index distribution of these 1.4 million quasars, because we have done it by drawing at random from these distributions, creating mock skies and measuring their dipole. The direction of the matter dipole, however, is consistent with that of the CMB. And this now has been confirmed. This was at about 4.9 sigma, because only 5 of these 10 million simulations that we did actually got up to the observed dipole. But subsequently, other catalogs, in particular radio catalogs, measured from the ground. This was from the Y satellite, our catalog. Now we have independent measurements on very different sources, which have also given a dipole pointing in the same direction and with an amplitude, in fact, even slightly higher, factor of 3 higher. Now, people have, as Tejinder said, people are now beginning to take this cosmic dipole anomaly seriously, because these are two completely independent sets of observations, very different systematics. Nevertheless, of course, you have to do all the checks. And in this recent review, in Reviews of Modern Physics, we have outlined all the ways that we could have misled ourselves. But we find that, in fact, none of them can account for this anomaly. It's not because of the cuts we employ. It's not because we are accidentally seeing some quasar close to us, which would be called a clustering dipole. There is clustering of the quasars, as we revealed by this power spectrum measured here in this work that was led by Sebastian von Hausiger. And you see that the power spectrum is actually in good agreement with our ideas about structure formation, which is called lambda CDM, but is actually really CDM, because lambda is unimportant on small scales. On large scales, the extrapolation of that is way, way short of what we measure. This is the expectation and this is what we measure. And there is clean water between them. And in particular, there is no other large-scale power. So concerns that have been raised that we are masking the sky so we could have contamination of the dipole, etc., they are unfounded. So let me speed up a bit now, because I've spent a long time describing that, but it's important to realize that this standard framework that is used to analyze the data is then suspect, and yet we continue to use it because that's the standard procedure. So the magnitude of the supernovae is called the luminosity distance in these units, and that is related to the cosmological parameters in the usual, using the usual Friedmann-Lemaitre equations. And so that's how we extract this parameter combination that I referred to earlier from the supernova data. Of course, that doesn't tell us the absolute magnitude, because we need to believe that that is the same for all supernovae. And to determine the Hubble parameter, we need to extend that mu-z diagram to the y-axis. It must intercept. But for that, you need the distance ladder. You need other objects like Cepheids to calibrate the supernovae and so on. The other point I want to make is that actually, strictly speaking, you don't really need to assume any cosmological model to analyze the supernova data, because you can just expand this luminosity distance in a Taylor series in redshift. And the first derivative of the scale factor is the Hubble parameter. That's the first term. The second term, defined in this strange manner, this was done by Alan Sandage, is in order to make this number positive when the universe is decelerating, which is what everyone expected it would be doing. And the third derivative is called the jerk, and so on. So we are normally going up to redshifts of just beyond 1. So this expansion is perfectly well behaved. There's no problem. In fact, in the JLA catalog, it is good to 7%, even up to the highest redshift. Now, as I've said before, the real problem comes in the statistical analysis because what these people were doing was taking the magnitude, subtracting from it the theoretically expected magnitude for the lambda CDM model, squaring it and dividing it by the observational uncertainty, but then adding this arbitrary error bar, which was allowed to float till you get a good fit. Instead, we introduced this maximum likelihood estimator, or people had also talked about the Bayesian hierarchical model, which just says that the likelihood is the probability, as you know, of the data given the model. And we can just factorize into two parts. One part that depends on the supernovae and one part that depends on the cosmology, because these two are independent of each other. The supernovae don't know what kind of a universe they live in, and cosmology doesn't know what supernovae do. So this is the very reasonable factorization. And here the hats refer to what we observe, and then there is the underlying model distribution, which is what we really are after. Now, we are actually initially going to do this work with Alberto Gufanti, who is an expert in using neural networks. This was back in 2014 when I was at the Niels Bohr Institute, and Jeppe Nielsen was my master's student. And we wanted to use neural networks, which are very popular these days, for doing things in a unbiased fashion. But Jeppe noticed that if you look at the actual distributions of the stretch and color corrections, they look pretty Gaussian. Now that saves us a lot of work because then I can just write down the probability of what I see. If I assume that the underlying distribution of these parameters is also Gaussian, which is reasonable, then all I need to do to evaluate this is to integrate a Gaussian, which I can do. And so I can calculate the likelihood in two lines and maximize it. And then I have my maximum likelihood estimator. I mean, you could do it the hard way. You could do this numerically and run a Markov chain Monte Carlo, but that is this Bayesian hierarchical model. But it's the same likelihood under the bonnet. But the thing
Sorry,
is
can
that
I
when
ask you a
you use
quick
that maximum
question?
likelihood, sorry,
Could I ask you a quick question?
please.
Yeah, if you could please go back to the previous slide. So are you saying that one could have chosen a sigma in square to fit a lambda equal to zero model if so desired?
You could make it bigger, and that was actually pointed out by someone called Vishwakarma, who used to work with Jayant Naldekar. That if you increase the error bar, you can fit anything. You can fit a dolphin, you know. And the thing is to ask: is this sigma in that is being added? Is that a reasonably reasonable number? The answer is that it was actually 0.13 magnitudes, which is roughly the same as the number by which the distant supernovae are fainter than expected. So,
Mm,
yeah, I think that is what raised alarm bells for us.
mhm.
So we can come back to that in the discussion. That's an important point that actually that number, that error bar. So it's like visualize I've set of data points and my theoretical model doesn't go through them. If I just stretch the error bars out, I can make it fit. But if I use the maximum likelihood estimator, then this banana in the lambda omega matter space, which was as so according to the JLA collaboration, actually comes down here. So JLA had put it up there with a significant lambda, but we found that in fact the contours now cross the line separating acceleration from no acceleration. So he wrote a paper which took some time to get published because people didn't want to hear about this. And it was called Marginal Evidence for Acceleration from Supernovae. And marginal means less than 3 sigma. So, of course, a lot of people then piled on and told us, as if we did not know, that, oh, omega matter is more than zero point 0.2, so you can't lie to the left of this line. Or, the CMB says that omega matter plus omega lambda is 1, so you have to lie on a diagonal here. Now, those statements are, of course, only relevant to this three parameter lambda CDM model. They're not true in general. We had shown the data like this simply to enable comparison with what had been shown before and to indicate what the effect is. But, that's how it goes. Notice that there are only 10 parameters in this fit. And in fact, the data is actually consistent with a uniform rate of expansion, which actually others had also remarked on if you average over the sky. Now, Rubin and Hayden criticized us because they said that the stretch and color parameters that we had adopted from the JLA catalog, that we had taken them to be independent of redshift, as shown here, because that's what the astronomers, the authors of the JLA catalog, had said themselves. And they, by the way, included all the authors of the supernova, the Nobel Prize winning authors as well. Every supernova astronomer in the world was on the JLA catalog, almost. But these guys said, look, if you look very carefully, you can imagine that there is a variation with redshift, right? And they can't do much for the HST data because the too much scattered there, but you can do it for the other three data sets and imagine fitting them with parabola. So this takes two parameters each. So that's 6 and 6, 12 parameters. So they add 12 more parameters to our 10 parameter model in order to allow for a redshift dependence and indeed model sample dependent light curve parameters. Now, okay, this to us it didn't look like this is justified to more than double the number of parameters in order to improve the evidence for acceleration. But I'll say this for Rubin and Hayden, they did the correct statistical analysis. They have a Bayesian hierarchical model and they reproduced with their model what we had done. Again, you see that this banana, this ellipse, is actually touching the acceleration versus deceleration line. This is just what we had got. So they reproduced our analysis. But then they said, if I put in this stuff, then I can move this thing upwards and save acceleration. I can again get back to where we were. But even so, the evidence for acceleration is still 3.7 sigma. It's still short of 5 sigma. And it, of course, opens a Pandora's box. If the light curve parameters are supposed to vary with redshift, then might the absolute magnitude also vary with redshift, perhaps? Now, at this point, let me quickly say what is being done about these peculiar velocities. So this redshift that is measured in the heliocentric frame is converted to the microwave background, assuming that the CMB dipole is entirely because of our motion. And so you take the measured value and multiply it by the redshift of the supernovae and so on, just relativistic transformations. And then you apply peculiar velocity corrections. So Ramesh did some detective work and determined what they were as a function of the redshift, these red dots. And what we discovered was that the redshifts, the peculiar velocity corrections, went to zero at a certain point, as if the authors of the JLA catalog had assumed that you converge to the CMB frame beyond that point. But in fact, the data don't show that. So we actually undid these corrections to get the original data in the heliocentric frame because we don't believe these corrections reflect the real story because they assume something which is not seen in the sky. And then we find that if you do a cosmographic analysis of the supernovae, which I've already talked about, but we allow one extra parameter. We allow the deceleration parameter Q naught to have a monopole term and a dipole term. Okay, we can't do a general multipole analysis because there aren't enough supernovae. Now, strictly speaking, you should do a covariant expansion, as for example, Asta Heinesen has proposed we should do, but that would already give you 15 parameters at this level. So, we don't have enough data to encounter that, to confront that right now. The data is coming. And you see, when I now plot, let my MLE loose on the data, it returns a strong dipole. The dipole, as you see here, is very strong compared to the monopole. The two scales are different. And here is standard lambda CDM, but the dipole is zero, and the monopole is about minus 0.53 or something. But in fact, the monopole now is much, much smaller. And the direction of this dipole is consistent with that of our local bulk velocity, or, here's the same dipole. You can tell from the spread just how scatty the data is. It's a 740 supernovae. But the significance of Q naught has now become very small. It's almost consistent with no acceleration. But there is a monopole component. One cannot deny that that could still be attributed to dark energy. But what it says is that the bulk of the acceleration is actually anisotropic. And so it cannot be due to anything to do with the quantum vacuum. Okay, because the quantum vacuum, of course, has to be Lorentz invariant, and or its effects have to be Lorentz invariant. At this point, Ramiz also looked back at the original papers from the Supernova Cosmology Project and the High Z Supernova Search Team, and found that most of the supernovae they had looked at were actually in the direction of the bulk flow. So, had they looked in the opposite direction, which is here, then might have come to a different conclusion. Now, at this point, we faced further criticism, and allow me 5 minutes to go into it because a lot of people assume that just because somebody has written a counter paper, that the original paper is thereby destroyed. As you are all professional physicists, you know that is not the case, but this seems to be widely believed in the community at large. So, what Rubin and Heitloof returned to do was to look at our dipole versus monopole, and this is from their paper. And the first thing they did was to recover our result, C19, Collin et al., that is to say heliocentric redshifts, which is this pink patch here. And as you see, we have a strong dipole and a small monopole nearly consistent with zero. But then they say, look, we must allow for this redshift dependence of the light curve parameters. And then you go to this green patch. As you see, the dipole does not change, but the monopole becomes stronger. This is just what you saw in that previous plot where they raised the banana. The next thing they say, why are you using heliocentric redshift? You should use the cosmic microwave background frame. Now, what that actually does is to simply flip the sign of the dipole. It doesn't make the dipole go away. Why does it flip the sign of the dipole? Because, as I showed you earlier, we are moving in the galaxy in the opposite direction to the dipole hotspot. So the dipole would still be there, but it would just reverse sign. And that is indeed what they see. Finally, they make corrections for peculiar velocity, which they want us to make, although we had questioned whether these are valid. And if you do that, then you see, then you get what the doctor wanted, which is that you have a zero dipole consistent with zero and a strong monopole, which is consistent with the standard model. Now, first of all, I don't think too many of you were actually aware that you have to do all this in order to extract evidence for isotropic acceleration, because the data are suggesting anisotropic acceleration. And in fact, subsequently, we have shown directly that the matter distribution is not isotropic in the CMB frame, because otherwise the universe would pass the Ellis-Baldwin test. In fact, it fails it. And Ramiz pointed out in a talk he gave at the Royal Society meeting a couple of years ago that we organized, that actually these peculiar velocity corrections that are being made, which is crucial, as you saw in this plot here, to get you what you want, that these are in fact pretty large, and locally they are as large as this 0.15 magnitude relative dimming, which is supposed to be the evidence for acceleration. So, in fact, you're making corrections to the data which are of the same order as the signal that is supposed to be your evidence for acceleration. So, let me fast forward to the conclusions because I see I'm already an hour, uh, taken an hour already. So when that analysis appeared, in Physics World ran an article on it, and they asked Adam Rees what he thought about it, and he said, "Oh, these guys are using old data. We have more supernovae now, and that doesn't show any anisotropy." The Pantheon catalog. And so he said, "Fine, we'll use the new catalog." And say, here is the Pantheon Plus catalog, the green, the redshift distribution. They have more supernovae at low redshift. And when you do quality cuts, we have 1700 supernovae. And now we find that the evidence for anisotropy is actually even stronger than before, and we do it in every frame. So the black points are the heliocentric frame, the cyan points are the CMB frame, which, as you see, reverse sign, but it's still a dipole, just as Rubin and Heitloof had noted. Then if I do it in the local group frame, the anisotropy is even more pronounced, these red lines. But if I do it in the CMB frame and apply peculiar velocity corrections, then the anisotropy is still there, but it is minimized. Okay, it's still not zero. And the direction of these anisotropies are all consistent with our local bulk flow direction. Now, what we can now do with all these supernovae is you can do tomography. We have twice the number, so you can do it in redshift slices. So that is what we have done here. And that is showing something very interesting, that this anisotropy dies away by a redshift of around zero point 0.1, which is just what you expect if it is really due to the local bulk flow and not due to vacuum energy. And in fact, to address the criticism of Rubin and Heitloff and Rubin and Hayden, we actually did it for both taking into account and not taking into account those stretch and color corrections dependence on redshift. And obviously, if we take into account those corrections, then the anisotropy is less pronounced, but it is still there. And I can come back to it later in the discussion. I want to mention that Kochsbang has done a similar analysis in her own way, not similar, her own analysis of the cosmic flows 4 data, and she confirms that the local value of Q naught actually fluctuates according to direction. And the monopole is interesting. I told you there is still a monopole, but that monopole could in principle be due to dark energy. But it's interesting that if I apply progressively higher cuts in redshift, so what you're looking at is the number of supernovae cumulatively increasing. And the monopole, which was positive, is now, as you see, becoming negative. So you're actually getting asymptotically deceleration, although locally it would appear to be acceleration. And this is also true whether it is the heliocentric frame, the CMB frame, the local groove frame, or the CMB frame with peculiar velocity corrections. In other words, we are not getting evidence for the standard model, which is excluded at high significance. It's shown here pictorially. This is the purple star is always lambda CDM in all these pictures. And you can see it's a long way away from the best fit to the data, whether we analyze it according to our method, or we also the C2 is our method, and C1 is the one that was advocated by Rubin and Hayden, which is that you allow for redshift dependence in those stretch and color corrections. But let me come to the punchline, which is what to end with in another 2 minutes. The latest development is that there is another correction that has now been suggested to the template by the Korean astronomers I mentioned, Son et al. And Chung et al. And so on. And they said that they find a correlation between the absolute magnitude of the supernovae and the age of the progenitors, the white dwarfs that you're talking about. Now, there is a debate about the age of the galaxy versus the age of the star and so on and so on. I'm going to cut through all that and just tell you what the correction they proposed was, which we added to the formula. And when we do that correction, then the magnitudes as a function of the redshift move from the from the red to the black points here. And when we apply that correction, now the difference with regard to what we had done earlier is that when we do that correction, then the dipole does not change at all. The dipole is the y-axis, but the monopole changes significantly. So the monopole, as you see now, becomes strongly positive. You see deceleration, whatever frame you analyze it in. In other words, the anisotropic part of the acceleration cannot be due to vacuum energy, and the isotropic part is actually a deceleration. So again, you don't need dark energy. Now, this has been challenged by a recent paper by Weisman et al., which the Royal Astronomical Society put a press release out about. They deliberately left out. It was initially meant to be a discussion of both our papers, but they left out our paper and focused just on them. To say that they had rebutted the argument of the Korean astronomers, but the Korean astronomers have struck back with this paper, which is currently on archive and also submitted to monthly notices. And they find that the trend that they had argued for is there because there are two opposing effects, which they point out in this text, which you can read later, that the reduced progenitor age evolution argued by Weisman et al. Must by the same logic be accompanied by steeper inferred progenitor age Hubble residual slope. And when you consistently combine them, you still see the same correlation, and the correction is unchanged from what we had used. But we can come back to this. The bottom line then is this. The cosmic acceleration inferred from supernovae is anisotropic in the heliocentric frame and points towards the cosmic background dipole or the local bulk flow, which are pretty close to each other. And that is just what you expect for tilted observers, as Christos Sagas had and his collaborators have argued for some years. Even after we boost to the CMB or local group frames, the cosmic acceleration remains anisotropic. Only if you correct for the correlated bulk motions of the supernova host galaxies can you start to get anywhere close to isotropic acceleration. But the bulk flow models that you are using to make these peculiar corrections, actually, there is no convergence to the microwave background frame. So these are inconsistent. And as an aside, the supernovae, which are beyond the range of these bulk flow models, are actually corrected assuming lambda CDM, the theory, which again is not confirmed by the data. So basically, there is a great deal of circularity in the arguments that are used in order to recover cosmic acceleration from the data. It assumes the model that you are actually supposed to be testing. Okay, so that's not a very healthy state of affairs, and there is a lot of discordance in the field, a lot of arguing back and forth, which I'm sure most of you are left bit bemused by, because as I just indicated to you in the past hour, there are lots of technical issues, and you would have to spend a lot of time familiarizing yourself with them. I've personally spent about 14 years learning about all this. To make progress, we'll need hundreds of thousands of supernovae, not enough to just have 1,000 odd. But this is actually coming. So the background to this picture is the first photos from the Legacy Survey of Space and Time on the Vera Rubin telescope, which has just started taking data a few weeks ago. And this, we are members of LSST, and we'll have access to the first data. And so I hope to report back to you in future on what the answer is. But I just want to show you that Ramiz's student, Animesh Shah, has been doing some forecasts for how well you can check whether there is indeed a dipole in the deceleration parameter. And you can see that the significance with which you can reject it is goes above 5 standard deviations if you have something like 2,500 supernovae, and we expect to soon have that. And therefore, we have to integrate this into the standard pipeline that is being used with this LSST, because they use photometric redshifts. There have to be other follow-up campaigns to get more precise spectroscopic redshifts. And so there is a lot of work to be done. But I think right now we want to simply get people to focus on this open issue that needs to be addressed with this forthcoming data. Above all, we should not use on this beautiful new data, we should not use an analysis framework that is past its sell-by date and that has been shown repeatedly to be biased and recovering essentially the answer that you want to recover. Let us do physics in a blind and in an unbiased manner. So let me stop there. Thank you.
Thank you. Thank you very much, Subir, for a beautiful lecture.
Thank you.
Uh, talk is open for questions, please. So before, while the hands come up, kindly just use your hand icon feature to ask a question. Subir, I wanted to ask you, in your conclusions,
Yes.
you are not making a statement about the monopole.
Oh, sorry. That is true. The monopole, whether it is negative or positive, depends, as I said, on whether you have the magnitudes are to be adjusted for the age of their progenitors. And I'm
Mm,
saying that if we follow what has been proposed by the Korean astronomers, then we
mm.
find that the monopole becomes significantly positive, right?
Yeah. Yeah.
But actually, it is positive. You can see it's marginal in most of these frames, but you can always find one in which is, for example, this one here, the CMB
Mm,
frame with peculiar velocity corrections. There it is slightly negative. Not as
mm,
negative as it is meant to be in the standard model. In the standard
mm,
model, it's meant to be here at minus zero point
mm,
0.5. The
mm,
actual monopole is more like minus 0.12 or
mm.
something, right?
So I
So in
think
any
the
case, it is much
uh,
weaker than
okay.
it is supposed to be in the standard cosmological model. Uh, but it in fact moves significantly to the right when you make that correction. So that also needs to be nailed down. And now that it has attracted so much attention, and with the forthcoming data from this LSST survey, I'm sure we'll have the professionals who know about these things will be able to establish it one way or the other.
So the dispute is not about the dipole, about the anisotropy, but about the monopole, right?
The
Right now.
dipole, the dispute is about both the dipole and the monopole, but they're being conducted by two different communities. So the
Mm,
people who question the dipole were, in fact, as I said, Rubin and Heitloof, his student. David Rubin is at Hawaii, and his point was that if we make peculiar velocity corrections for the host galaxies of the supernovae, then you can make the dipole disappear or get sufficiently close to zero that you don't worry about it. And what I pointed out was that the corrections that you make thereby are actually not, the framework in which you make those corrections is not consistent with other observations. In particular, the cosmic dipole anomaly, which I've talked about, is not
right. So
consistent.
what is their stand on the quasar dipole
Oh, they don't
anomaly?
have a stand because that data came afterwards. So we have not
Okay.
had the Rubin Heitloof paper was before that. It was
So
in
you
response to
cannot
what
have
we did
you
in
yeah.
2019.
You cannot have a dipole anomaly in the quasar distribution, but not have it. I mean, if it is there in the quasars, and you expect it to be there in the supernovae also,
Well,
right?
the way I would put it is that the basis for making the peculiar velocity corrections of the supernovae host galaxies is a framework which has been falsified by the quasar data. That's the way I would put it.
Hmm.
Right. However, to be fair, almost all analyses today are still being carried out assuming the standard cosmological model in which the distribution of matter is isotropic in the frame in which the CMB is isotropic.
Hmm.
For example, the analysis of the DAISY data, which is arguing for a time, redshift varying dark energy and so on, or the
Hmm.
analysis of the weak lensing data from the dark energy survey, and every set of data is being analyzed using the same model, the standard Friedman, Lemaitre, Robertson, Walker model, which we believe has been certainly significantly challenged, if not totally falsified, by the cosmic dipole anomaly. But the cosmic dipole anomaly has not yet been, I think, totally accepted by the community because they're still using a model that it has been falsified by. So they would rather choose to think that there is some systematic error somewhere, and so you don't need to take it seriously.
Okay. So in principle, let's say the quantum vacuum is lambda is zero. Let's say it turns out that it's zero. But even then, in principle, one could have a acceleration, right? Which uh, can be consistent with your anisotropy. A
No,
tilted
you
universe
cannot have
doesn't accelerate.
anisotropic acceleration due to anything to look. The whole
So no
reason
lambda.
people have
Lambda
taken,
zero quantum vacuum does
yeah,
not contribute to
yeah.
in cosmology,
Then what
but
does? What is driving the acceleration?
I will, let's say I will come to that. That's a theory question. One day we will come to that. But
Sure.
data
Yeah.
and isotropy, namely a tilted universe in your language, which is
Yes.
accelerating, is
That
not
would that
ruled
would give
out.
the perception of acceleration in a particular direction, even though the globally the universe is not accelerating. It's a local phenomenon, simply because we are not ideal observers in the global universe as is usually assumed. Can I quickly answer the question that Andrew has typed into
Yeah,
the
yeah,
chat
yeah.
box?
Please go ahead. Yeah,
Sorry,
can you
Andrew,
say
do you want to
that?
ask the question?
Sure. Hi,
Yeah.
Subir. Nice to see you. And that was a delightful talk, and it's absolutely delightful to see people pushing on standard paradigms which become embedded in the community, and one loves to see them really tested properly. So this is how science should be done. But
Thank you.
I have a very simple and naive question, which is
Yes.
your dipole, and you can see it on the graphs that you show,
Yes.
varies wildly according to the which analysis you approach. And so how does that exclude a zero dipole? It looks like the error bars could easily accommodate zero dipole.
Sorry, which plot are you referring to? I can keep scrolling back
Those
till I get to the one you want.
No, this is
Okay.
fine. The
Yeah.
ones that you've
Yeah.
got four models there,
Yes.
and in two of them it's plus, and two of them it's minus
Yes.
the dipole.
That's because of that plot. Okay, then I'll have to go back to show you. Actually, uh, I have to go to the actual slide. So give me a second. I think, yeah, continue to share this window. Can you still see my window?
No, now we
I can
see
see
just
you.
the
Oh, sorry. Let me start sharing again, and let me just get to that slide, and I shall show you what I mean by that. So the reason for that is simple kinematics. So let me go back to share and choose. Yes. Now you should be able to see something on the screen.
Yes.
Yes,
Yeah.
yes.
So the reason for that, Andrew, is that the different frames of reference that those four plots show, in that our local velocity is different in all of them. So in the heliocentric frame, we are the frame of reference of the solar system, which, as we are in the Sun-Earth system. So basically, it's the sun. But when we boost to the CMB frame, that is boosting in a certain direction at 370 kilometers per second. But actually, we are going back in the galaxy in the opposite direction compared to with respect to the hotspot in the CMB. Okay. So if I imagine the CMB frame
I
is
mean,
on the right hand side.
my impression is, and
Yeah.
maybe I've been out of this for a little while, but
Yeah.
my impression is there is a frame where the dipole in the CMB seems
Yes.
to vanish entirely.
Correct. And that frame you
And
get to.
and
Yeah.
then
So
once you've got to that frame, what
Yes.
you're really saying is that the supernova that you see have a dipole with respect to that frame, and that's the language that
Yes,
should
yes.
be
So
used.
we are looking. So the point I want to make is that our actual velocity uh, is not 370 kilometers per second. It is in fact 620 kilometers per second. But
Right.
half of that is being cancelled out because we are within the galaxy moving backwards with respect. Oops, I didn't mean to do that. We are moving backwards with respect to the CMB hotspot. This is just the way it happens to be. Okay.
Yes, yes, I know, but that is the CMB frame, the one
Correct,
that's
correct.
370
Correct. So
kilometers per second
if we
corrected.
boost, yeah, right. So if we boost with 370 kilometers per second, then we get to the frame in which the CMB is isotropic, and we call that the CMB frame. However, the supernovae are in galaxies which still have peculiar velocities with respect to that frame. Just as we have a peculiar velocity of 370 kilometers per second, the supernova bearing host galaxies also have peculiar velocities. So you need to correct for the supernova host galaxy peculiar velocities as well. And that is this frame, which you can call the cosmic rest frame, or whatever we call it, the HD frame in recent literature. For HD stands for Hubble diagram. So in that frame, you would expect to be able to apply the Friedmann-Lemaitre equation to the magnitudes and the redshifts. After you have boosted the magnitudes and the redshifts by doing two transformations, both
Right.
special relativistic, one for our peculiar motion with respect to this cosmic rest frame, and the other for the peculiar velocities of the sources being observed with respect to the same rest frame. There are two sets of corrections, right?
Right.
So
So
if I now go
is
back,
slide number 19, is slide
yes,
number 19 the bottom line,
yeah,
basically?
19,
Yeah, this one.
yeah.
So
No,
that's basically the evidence.
so the evidence, the data does not agree that we are actually converging to the CMB frame.
I'm going to make some stupid
Yeah.
remark now. This looks
No,
like
please do.
Vera
I would
Rubin's
love to have you
constant.
comment on this. Yeah. By the way, I'm
Looks
showing
like
here this plot.
Vera
which-
Rubin's constant velocity curve.
Yeah. Yeah. Sorry?
It looks like Vera Rubin's constant velocity
No.
rotation
Actually,
curve of
you're right.
galaxies.
You could draw a horizontal line. Now, I have taken this
Yeah.
plot actually from a paper that, in fact, did not draw the conclusion that I'm drawing here, because they only showed the data that is, in fact, imprinted on this plot. I have added the points in red subsequently. They came after this plot was made. And in 2021, subsequently came the Sloan data, SDSS data, which is this red point here, 313 plus minus 80. And then came the Cosmic Flows 4 survey data, which are these three red points here, the most discrepant being the 419 plus minus 36. And I'm well aware that there is a dispute about exactly what is the significance of this discrepancy, how you take into account, because it depends, of course, on what distance I put them at. And these distances, I mean, there should also be a horizontal error bar, which is the uncertainty, as you know, in the distance estimates, if they're Tully-Fisher or fundamental plane or whatever. So I mean, all that would make it an extremely complicated plot, but I'm just saying it in words. You could argue that the discrepancy is not as severe as it looks like superficially from this plot. It's something that one could perhaps live with, right? However, I think what this plot does do, as Rick Watkins and collaborators have emphasized, is that it makes a strong case for getting more peculiar velocity data, proving out a bit deeper, getting better distance estimates, trying to nail this thing down. Because this does not by itself look like you're converging to the CMB frame. And indeed, nobody, let me turn the statement around, nobody to my knowledge would claim that we have shown demonstrated convergence to the CMB frame. And yet, we continue to use for analyzing other data, baryon acoustic oscillation data or weak lensing data or whatever data, we continue to use a theoretical framework that assumes exactly that, which is not at all evidenced by this plot.
Thank you.
Now,
Thank you.
I should
So-
say I'm not an expert in peculiar velocity measurements. I know they're very difficult. At one time, I was told there are only 10 people in the world doing that. And actually, sadly, two of the more prominent ones, in fact, had tragic accidents while they were observing. So it's not a very crowded field, is all I'll say. I think more people need to do these measurements. But you need to motivate difficult work by pointing out what the payoff is. The payoff is, as you quite rightly emphasize, are we actually following that purple curve? Are we converging to the CMB frame as we should? Of course, there will always be a small residual, there is always a cosmic variance. We are in a Gaussian random field. You're never going to get to zero. But are we sensibly homogeneous? I see there is another question.
The
or
hand
somebody
up,
has raised their hand. Yeah.
the name says iPad. I'm sorry, I don't know your name, but kindly go ahead and ask your question.
Yes, I do apologize for being called iPad. Sarkar has already recognized who I am.
Yes.
And I am a particle physicist, not a cosmologist.
This is, for everyone concerned, this is Professor Alvaro de Rula from the CERN Theory Division, now emeritus.
That is correct. Thank you for...
Great to have you with us, sir.
Thank you. Thank you for what you say. Now, as a particle physicist, I have two remarks to make. One is that the analysis of the data is horrendously complex and therefore very difficult to follow. But the more important point is that the original conclusion that the universe was expanding in an accelerated fashion comes from an analysis of data in which you arbitrarily increase the error bars till the expectation that you want to reach is
Yes.
reached. That's
Yes.
absolutely amazing. This, for someone who is not a cosmologist and therefore not used to this kind of analysis, it's absolutely amazing. Absolutely amazing.
They make no secret of it. It is actually dignified with the name adjusted chi-square method. It's there in print in the journal. So you might well ask why the referee did not question this, because, if I mean, for all the reasons I gave, but there you are. It continues to be used. And it is not clear to many people that when we first published a paper saying marginal evidence for acceleration and it caused a huge stink, we are simply objecting to that method. I mean, we had not introduced any astrophysics at all. We simply introduced a maximum likelihood estimator, and this one here. And actually, it was already in the literature. It had been introduced by Roberto Trotta and collaborators as a Bayesian hierarchical model. But the fact that it leads to dramatically different conclusions, this had not been emphasized. And I realized when we, put this out as a paper, why people had been so circumspect about it, because it took us 16 months to get this paper published because people didn't want to hear about this, even though it was a. But as I said, I should make a remark now. I feel a bit bad about that. Mr. Jeppe Nielsen, who was one of the best students I've ever had, he did this as a master's student. He left physics because he was very upset that the Nobel laureates who had done this acceleration work commented on social media that we were using unorthodox statistics. And Jeppe said, how can they call the maximum likelihood estimator unorthodox? So I said, I don't know, Jeppe, maybe they're not used to it. I don't know. I mean, this standard, as you know, industry standard procedure. But Jeppe was so horrified that he left physics. He's working for Danish military intelligence now. So,
I
I
know,
mean,
I know of examples of that kind, of leaving a certain type of physics because of
yes,
the reasons that your colleague did.
yes.
In astrophysics, this is absolutely not exceptional. I thought
Well, indeed.
in cosmology,
I'm aware of your own experience with your work on gamma ray bursts, etc. Yes. But the point is that, I think we have to persevere because in the end, there is only one way to, I was going to say one way to correctly analyze the data. There may not be a unique way because statistics is also not a formally absolute science, but we are physicists. We know how to do things that make as good sense as possible under the circumstances and given the constraints. And we draw conclusions that are as robust as is possible. We don't worry about the mathematical issues to do with statistics. So, I mean, it just boggles my mind that people are not aware that in this business there is such a kind of a body in the closet, as it were, which has to do with simply the difference between doing this adjusted chi-square and using a maximal likelihood estimator.
So, Subir, could I ask you at this stage,
Hmm.
suppose we have more data, like you said, in the future, thousands and thousands of
Hmm.
supernovae,
Hmm.
will this dispute be resolved and your answer independent, whether you magnify sigma n square or whether you use maximum likelihood
No,
estimate?
actually, the point is that I wanted to show you this plot. This was done after our paper. This is the group from Imperial College. Actually, Van Dyke is the head of the statistics department there, I believe. And they used their so-called Bayesian hierarchical model, which is actually exactly the same likelihood. And as you see in this plot, what they got, which are these jagged contours, which are basically fall on top of the ones that we derived in two lines because we have a analytical likelihood. Their chains had not yet converged on the 3 sigma one, but you can see that broadly they are in agreement with us. They're doing it numerically, but they get the same result. Whereas these ones up here, that is what the JLA people got by doing this adjusted chi-square. So it is not that there are people in the community are unaware of this. And as I also pointed out, Rubin and Hayden, in fact, are also using this Bayesian hierarchical model, the right way to
Hmm.
do the statistics,
Yeah.
because only then they could have recovered our result,
So,
right?
but then why do we need more supernovae in the future? We just need to do the
Oh,
statistical analysis correctly.
you need to do the statistical analysis correctly. You need to determine if indeed the absolute supernova magnitudes are correlated with other aspects of the progenitors, such as their age, or like I mentioned, the I don't know, the metallicity of the host galaxies, or the distance the supernova is from the galactic center, or any one of a
Yeah. So,
number of
so, so my,
environmental
my question
parameters.
is, can it be that the people who use sigma in square in the future, in the light of more data about
Yeah.
progenitor, could they also be forced to turn around and agree that it is not accelerating?
Well, I should hope so too. But sigma end is, if you like to borrow another phrase, it is the unknown unknowns. That is what it is supposed to represent. And sure,
Right.
there are always unknown unknowns, but you don't expect that sigma to be as large as the signal you're looking for. Because I've talked to supernova astronomers, and they say that their estimate of what the unknown unknowns are would be something of order of at most, half of that, zero point zero 0.07
Mhm.
mag. They're
Okay.
using 0.13 mag, right?
It
Which
would have
is,
been nice if, like, for example, Anthony Lazenby was here today. I was talking to him in the
uh,
previous OSMU talk. I asked him about your latest monthly notices paper, and he
yes.
did say that he agrees with the original blah 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 analysis. So it would have been nice to have a debate, a discussion. And I'm not saying I am disagreeing with you. I just want we want to
No, no.
understand,
So original
listen
analysis
to
of what?
the two supernova teams which got
Oh,
rid
I
of the
see. I see. Well, we have not done anything new here. We have used the correction that was proposed by the Korean astronomers, which is
Hmm.
this correction of delta mz according to. So, as I outlined, the supernovas, okay, the establishment supernova astronomers, if you like, they already say that this X1 and C are dependent on redshift. Now,
Hmm.
therefore, they should not have any ideological objection, if you like,
Hmm.
to somebody else coming along and saying there is also a correction dependent on the age of the progenitor star, if they can establish that statistically from the data. Now, if you look at this data, the correlation is obviously there's a huge scatter. The question is that slope significantly different from zero? This is what the debate among the astronomers is about, right? And what
Right,
the
right. I
Koreans are
agree. I
saying,
agree.
the
This is the
Koreans are
point
saying
Anthony
that,
was making. Yes. Sorry.
yeah, but the Koreans are saying that the logic of that has been proposed by this Weisman et al. Paper, which was got a huge publicity from the journal that published the paper. In fact, the press release even said that they have disproved or rebutted the wrong claim by the Korean astronomers. Funnily enough, the Korean astronomers had also published in monthly notices, and that too had a press release by the Royal Astronomical Society. So I'm looking forward to when their latest paper, which is submitted to the same journal, gets published. We'll see what they then say. But what these guys are saying is that there are two effects which work in opposite directions, as I have said here, this part here, right? And that net effect, therefore, it cancels out. Now, this is something that, as I said, I do not want to comment on because I have not done this work. It seems to me that what the Koreans are saying makes sense, and this is the data here. So you can see for yourself that if you choose a much larger redshift interval than is relevant here, then you can reduce the slope, make it consistent with zero, increase the scatter, etc. But that you actually get the kind of correlation that they argue for if you do it in a consistent way.
Thank you. Yes.
Yeah.
Professor Derula, do you have more questions?
I think he's still there. Alvaro, did you want to say something more, or is that it? He must have
Uh,
left his room. Yeah.
yeah, so just a little side question, Subir. Just today saw this Nature paper from last month, Labini and Gallopo
Yes.
gigaparsec scale structures. Do you have some that looked interesting? But I also saw that someone has rebutted the claim as being in error.
That's correct. Siloslavini and Gallupo analyzed the DAISY data and found, and using a statistic for correlations, which is got angular sensitivity, they pointed out that there are long filaments
Hmm,
extending to gigaparsec scales, which would be a pretty, prima facie violation of cosmological principle.
hmm,
Subsequently, Till Sawala, he is a cosmologist in Helsinki,
hmm,
he did some detective work and he points out that he thinks these guys have confused two measures of the distance. They have confused the co-moving distance with the luminosity distance. So there is a factor of 1 plus z over h involved. And that factor means that Siloslavini and Gallopo have overestimated the scale of their structures by a
hmm,
factor ranging between 1.5 and 1.7 for the
hmm,
two for the catalogs of objects they've looked at, right?
hmm,
So if you take if that is correct, and one should really wait for the response from Siloslavini and Gallopo, then indeed the discrepancy in the scale is reduced. However, Till Sawala says that the what they are, the SDS, sorry, the DAISY data is consistent with the simulations of lambda CDM that he's using. They're called the Flamingo simulations,
hmm,
but he is only using the power spectrum to make the comparison, and the power spectrum has got no angular information in it. It's averaged over
hmm,
all angles, so it will not be sensitive to the kind of angular correlations that Siloslavini and Gallupo have emphasized, right?
hmm, hmm.
So I
Right.
am eagerly awaiting the response from them to
Hmm,
show whether the statistic they have used is still inconsistent with the expectations in lambda CDM, even
hmm.
if the extent of the structures is about 50% less than what they had initially thought.
Okay, okay. Thank you. Thank you. Very, very nice. So,
Yeah. I should say that I have discussed this with Francesco Siloslavini. So
mhm,
I'm saying that what I just said is on the basis of our discussion.
Thank you. I had another slightly side question. I understand that lambda part is being questioned. I would question also the CDM part because, and I want your views on that. My picture for some years has been that galactic dynamics, rotation curves, Bernoulli Fisher, and radial acceleration relation are all much better explained by Milgrom's Mond than by CDM, but CMB peaks are better explained by some form of dark matter. It says sterile neutrinos need not be, uh, doesn't have to be CDM for CMB peaks. So it seems that a hybrid dark matter MON model does well on these two aspects, and also because in MON structures grow faster than in lambda CDM, there is a possibility of developing a tilt of the kind, the dipole anomaly of the kind you're seeing, while starting from CMB peaks and CMB level. At the CMB level, let's say FLRW holds. But since then, structures can develop so fast that the tilt appears with like this anomalous bulk flow, which is disagreeing with lambda CDM, but uh, there may be some other model which can explain it.
Well, my view about dark, first of all, I want to say it's given the number of given that most of the community, I would say, 95, 98%, maybe 99% of the cosmologies community, I'm talking about professional cosmologists, they believe that lambda CDM has been established beyond doubt. I think it is sensible to take one problem at a time. That's as far as I'm doing, but I can give you my personal view about it. My view is that obviously one should look at alternatives to general relativity in order to understand when we have discrepancies such as that which leads to the notion of dark matter. There is a historical precedent for that. In fact, it is well known that you can actually fit rotation curves of galaxies without invoking dark matter. But as you said, the real crux is the formation of structure in the universe. And given the amplitude of the fluctuations in the microwave background, if you want to create the amount of structure that we see today, then if we assume the standard growth rate of fluctuations, which is, I think, Lifshitz first calculated, fluctuations grow proportional to the scale factor in a expanding universe instead of
In GR, in
in GR, yeah, yeah.
non-standard GR.
Yeah, because they would normally grow exponentially in flat space time, but here they grow proportional to the scale factor. In that case, given the initial amplitude of the fluctuations, you don't have enough time to create structure today, and that is why we invent dark matter so that it comes to dominate the universe at a redshift which is about 5 or 6 times higher, and then there is enough time. That is the real argument for dark matter. Another way to put it, and this is something that actually is more relevant today, is that if you had no dark matter, if you had only baryonic matter, then you would have very pronounced oscillations in the correlations on the galaxies. These were actually, I think, originally called the Sakharov oscillations. I should confess, I've never managed to find the paper by Sakharov where he talked about this, but maybe there is one. But what we today call the baryon acoustic oscillations, which are only about 1% in amplitude, would have been order one. And I think Scott Dodelson and forget the co-author's name, they wrote a paper in PRL pointing out that if you had a universe without dark matter, then the baryon acoustic oscillations would be huge, much bigger
No,
than
but
we see them
MOND,
today.
MOND plus sterile neutrinos,
No,
with
now there. So let me come to that.
MOND also arrived at anisotropic gravity. In principle, that's
Sure, sure. So
possible.
now, if you want to, so basically, what we are saying now is that the simple-minded idea of Mond, which is just a empirical rule for how to calculate dynamics when the test particle acceleration falls below some new value of nature, 10 to the minus 10 centimeter per second square, that is not enough to address structure formation. For that, you
I
need
agree.
a theory.
I agree.
Now,
Yeah.
now, as we all know, a theory of Mond has been hard to construct for obvious reasons. You can always construct a test model, I mean, a toy model, which can give you what you see on the sky, but mapping it to a physical model has proved to be quite difficult, which is not to say that such a thing does not exist. But really, the amount of work that has been invested in looking at such a physical realization is really a tiny, tiny, tiny fraction of the amount of work that is devoted to doing quote precision cosmology, right?
Yeah.
Uh,
Thank you.
so, so so I would like to see more people look at this. But let me just
Uh,
quickly say the other aspect is this growth rate. Now, the
right.
growth rate may indeed be different. In fact, might be different for tilted observers. That is something that Sagas is also looking at. And we might therefore need to revisit our ideas about just how much dark matter is required by structure formation. But you need to do a fair bit of work on that because the part of lambda CDM that, to my mind, is best developed and the most elegant in a way in terms of confrontation with observations is the theory of structure formation.
Yeah,
Okay,
but if
there are
now you have a
assumptions
tilt,
made.
so we have to explain the
Yeah,
tilt.
yeah. So I agree, but I'm saying that just as a honest broker, it seems to me that whereas lambda is absolutely ugly to me, that it is I can't believe that lambda can be of order h Hubble parameter square, but. the fact that if you start with the Gaussian random field and then you have the usual growth rate of fluctuations, that you get this cosmic web in the sky that looks pretty much like what we, uh, you
Yeah.
know,
Yeah, I agree. What
what we
I'm
see in the
saying, Subir,
simulation.
that
That is that,
yeah,
yeah,
dark matter need not be cold dark matter. It
yeah,
can be sterile neutrinos of say few tens of eV
yeah.
with a hybrid with a MOND, and
Uh,
that is an interesting model. Are you frozen, Subir?
no, I'm not frozen. I can hear you. I'm sorry. I was
Yeah,
just
yeah. So,
reading. Alvaro has now pasted something into the chat box.
no, I think is
Uh,
that from Nathan? That I think that's
yeah,
from Nathan.
no,
But I
this.
think you go ahead to the other questions. To
Yeah.
Alvarez has a question, I think, and I think that post who has posted? I think Nathan has posted something from Peebles. Oh, that's gone. Is it? No.
No, no, the comment by Nathan is still there. And maybe,
Yeah, yeah.
Nathan,
So
do you want
sorry,
to speak
Nathan,
to
not.
this?
Maybe
Hi,
first you
Subir.
take Alvarez's question, and then Nathan
No,
can.
no, Alvaro has a question?
No, Alvaro has an answer. You
Oh,
you asked me whether I would like to say something more about
yes,
the way these data were originally analyzed. And
yes,
the answer is yes, I do have something more to say, but I'm too
please.
polite to say it.
Please go ahead. Go ahead and say
All
it.
this is being recorded and will be put on YouTube, Alvaro.
This would be
Yeah, please go
impolite.
ahead and say
So
it. Yeah.
I'm going to shut up.
Yeah.
No, please go ahead.
No, please
No,
go ahead.
this has been long enough to go into a sideways discussion, which is more on the behavior of humans than on science itself.
So, sociology, yes, we inevitably get to sociology, yes.
There was
I don't
also a
want to discuss
question
this
in the
other.
audience, can a Nobel Prize be recalled? I don't think anybody has to answer it, but a question was there in the chat.
Yes, yes, that was Petros, I think. I
Yeah,
don't know if
yeah.
he's still online. The answer is no. I don't know. I actually I don't know, but I don't believe, as you say, it has it. Well, let's draw a veil over that, and I don't
Yeah,
want
yeah.
to,
Yeah, Alvarez, please go ahead, complete, and then we'll come to Nathan. Yeah.
No, I want to say anything else. I think
yeah,
Okay,
my
okay.
advice
Thank
would
you.
be
Thank
to
you.
stop the discussion now. We have been discussing for a long time.
yes,
It's poor Sarkar deserves a glass of wine.
Okay, Nathan, please go ahead.
Hey, Subir, this is a
yeah.
real
Hi.
talk. I just no, I was just following the previous discussion about
Yes,
all flows and the expected evolution to the modern epoch, and it just seems to me
yes.
like the main sort of the biggest sort of back of the envelope argument against it came from Jim Peebles in his review in 2022, and so I just thought it was relevant to post just for the sake of playing devil's advocate to post that little blurb from
Could
the
you
review.
please show Peebles' statement? I didn't get to read it.
There's a screenshot in the chat.
Yeah.
It's
So
in the chat.
I could read it out if you like. It says several other points are to be noted. First, the general conclusion has been that uh, within the standard cosmology and to a reasonable degree of biasing in the positions of quasars and radio galaxies relative to the mass, comma, intrinsic inhomogeneity is not a likely explanation for the anomalous dipole anisotropies of these distant objects. Uh, This might be checked by the cross correlation between the surface mass density indicated by the CMB lensing with the positions of distant radio galaxies, but I have not found a discussion of the test. I have something to say about that. A simple order of magnitude argument is that if quasars and other radio galaxies were useful mass tracers on scales approaching the Hubble length, then the observed dipole anisotropies of 2%, delta n by n of 2%, would have produced a bulk flow of the order of 2% of the speed of light, which is absurd. So what Peebles is saying is that uh, I mean, something that one would, of course, agree with, that we cannot interpret the anomalously large quasar and radio galaxy dipole as due to a high velocity because these guys are at such distances, these quasars and dipoles, if they're at cosmological distances, which is tens of thousands of megaparsecs, then the corresponding fluctuations in the matter have to be huge, and the velocities would have to be huge in order to produce the anisotropies that we see. So it must be something different. It is not just, already the bulk flow that we are seeing on the sky. In order to account for that, I'm talking about the picture that I already showed. You need the great attractor or whatever the hell it is to exceed 10 to the 17 solar masses in order to be pulling us at few hundred kilometers per second from beyond a distance of 300 megaparsecs. It's just 1 by r square law. Now, of course, that's a rough estimate. The object might be extended, so it's not exactly 1 by r square, etc. But that's the kind of thing you are up against. But the point that Peebles makes is that this suggestion that he makes, that you could look for the cross correlation between the mass density indicated by CMB lensing with distant galaxies positions. The problem is that CMB lensing, which is something that has been now done beautifully by, for example, the Atacama Cosmology Telescope over a fairly large chunk of the sky, that's measuring the integral over structure formation all the way from us all the way back to the last scattering surface. So it depends on the nature of the dark matter, or whatever the growth, put it more, depends on the growth rate of the fluctuations. And it, of course, depends on the integrated column density of matter. And my first thought when we found this anomalous dipole was, could we not see this in the lensing data? Could we not see in the CMB frame, after boosting to the CMB frame, an anisotropy in the CMB lensing? We are talking about a tiny effect. We are only talking about a 1% effect at most. But it turns out that the way that the data is actually being analyzed and the estimators that they use, well, at least Sebastian Hauseger told me that, in fact, you can't actually look for such a thing because the dipole, they're not sensitive to the dipole. That's the way that data is analyzed. So I don't think that but Jim is suggesting a cross correlation between surface mass density with the positions of radio galaxies. And as he writes, he has not found a discussion of this test. I don't know if anybody has figured out a way to do it. That's something. So I think we do need to think about independent ways of checking all this. And I'm very happy that someone of the stature of Peebles is proposing such tests. There are hundreds of smart young people in cosmology who are all spending their time doing forecasts for lambda CDM. I think they would find perhaps it more rewarding if they got onto these kind of tests, and they might find something new and startling. So,
by the way, Subir, I wanted to mention, sorry to interrupt you, that
yeah,
you said that you find the lambda part of lambda CDM ugly. I
yeah,
should confess, I find the CDM part ugly.
yeah. Well,
I'm okay with
we,
DM, but I'm not okay with CDM.
no, look, I have to say, I'm a particle theorist as well, and for such CDM is actually kind of plausible because you expect that there could be a new stable particle in nature. Of course, there is no reason why that new stable particle, even if it exists, we have no evidence for that yet, should
Yeah.
have a relic abundance of the order of the dark matter. And I've often said that it is kind of curious that the dark matter, even if it has a completely different origin than baryons, has something of order the same amount of energy density today. That strikes me as also a coincidence, similar to the one that lambda is of
Yeah,
order
I
h
agree.
square.
How about
Yeah.
sterile neutrinos?
Sterile neutrinos, unfortunately, you have no evidence that they exist. They could, in principle,
No, it's
exist,
the
and you
same
can.
as CDM, same as CDM.
Terasidium, but we have been looking for sterile neutrinos. I'm part of the IceCube experiment. We have looked very hard for sterile neutrinos because we can see if the regular neutrinos are mixing with them because then the fluxes of the regular neutrinos will be different from the ones that we measure. We have found no evidence for it. There were various false alarms raised over possible detection of sterile neutrinos in short baseline experiments on Earth, but they have all disappeared. The most prominent one was from Los Alamos, the so-called that was an anomaly that lasted for maybe 20 years. But quite recently, the microboon experiment at Fermilab appears to have excluded that.
But
So
you don't rule them out entirely, right? 3 generations of
well,
sterile.
you can, of course, if you have an arbitrarily small mixing with the regular neutrinos, then you can't rule anything out because unless there is that tiny mixing, you can't create them, either in the early
Because
universe or
why
today.
I'm saying this is that I've been studying these left-right symmetric models coming from octonions and algebraic unification.
Yes.
Sterile neutrinos are extremely natural. They complete the standard
Sure.
model.
Sterile neutrinos
And
are very natural because it's not at all necessary that everything should be a doublet of SU2 cross U1. So anything which is a singlet under that is by definition that is what we call sterile. It has no gauge
yeah,
interactions.
yeah,
You are
right,
talking about actually neutrinos that would have gauge interactions, but the right part is at a much higher energy scale, so they're very very weak. Uh,
right.
but but we know that that scale is at least of order of 60, 100 TeV. Otherwise, you would have already seen the effects of those models are good models. They are prescriptive, they're falsifiable. So they have lots of impact, not just sterile neutrinos, but on other things. You can
But
set
in my picture, the right-handed sector, the SU2R, is not a right-handed weak interaction. It's actually gravity. So
well,
there, the coupling.
I must interrupt you there. If it is most plausible, so the only way we characterize dark matter is by saying it has gravitational interactions.
Right.
If it had only
So
had gravitational interactions and no other, then you'll never detect it any other way. And
uh,
we try to give it some non-gravitational interactions
yeah,
because otherwise you'll never be able to independently
yeah, but
detect it.
the sterile neutrino might be a beast like that.
Well,
So
I tell you, years ago, I wrote a paper on gravitinos in supergravity, and in fact, it looked very plausible as a dark matter candidate. And my, co-author John Ellis said to me, "Don't highlight that in the paper because all the dark matter experimentalists will hate us if we say that the dark matter is a purely gravitational interacting particle because there is no way to detect it." Right? And in fact, we didn't do that, although we did have a footnote in that paper from 1985 saying that gravitinos could be the dark matter. And lo and behold, 20 years later, gravitino dark matter became a thing. Everybody was writing papers about that because you can't rule it out and you can sort of talk about it till the cows come home. I mean,
Mhm.
but yeah, so to summarize, I'm concerned about dark energy simply because I think it is a much more of a fundamental challenge to uh, our current understanding in terms of quantum field theory, etc. I mean, I have no solution for the cosmological constant problem. Nobody has. But if we could say that there is no experimental or observational evidence that lambda is non-zero, and in fact that it is very close to zero, but not quite so, then it would have huge impact on fundamental physics because people
Yes.
doing uh, considering fundamental theories of quantum gravity, etc., none of which have so far been able to address the cosmological constant problem either. They are, however, very concerned about whether the vacuum state has got a non-zero lambda or not, and that
Mhm.
informs much of the discussion for string theorists. They basically, because as you know, their most favored ground state would actually be one with negative cosmological constant, and then they bend over backwards to make it slightly positive, and then they realize that it should not be a constant; it should have a slope. This is the swampland program.
Mhm.
And then they love it when astronomers tell them, "Oh yeah, we have found evidence for evolving dark energy and so on." Because then, and to my mind, it's all nonsense. I mean, okay, I'll make a strong statement. We have gone over an hour in the discussion. I think it's all nonsense. It's people being misled by one badly observed supernova will give you some a completely unphysical answer, like an equation of state more negative than -1. And people do not put priors on their analysis to exclude unphysical possibilities. For example, violation of unitarity, or as I emphasized with the anisotropy, violations of Lorentz invariance. These are not part of the toolkit of astronomical analysis. They do not impose what theoretical physicists would agree are sacrosanct. Causality is sacrosanct, unitarity is sacrosanct. If those are to be violated, then we have no basis for discussion.
Thank you, Subir. Unni has a question for you.
Yes.
Can you read it in the chat?
It says, even if the acceleration turns out to be zero or a deceleration, the inference that there is unseen uniformly distributed matter with a density of about zero point 0.7 in the critical universe is robust, isn't it? Well, only the answer is that inference largely comes from consideration of structure formation, for which indeed you would need, largely cold dark matter. But then you can question whether the growth rate that is assumed for that is indeed correct, and that is something under consideration now. Because if the growth rate were faster, then you would not need the dark matter, for example. And secondly, if the law of gravity were to be different in very weak fields than Newtonian, then again you would have to reconsider the matter. And I would remind you, and you know this very well, but not everybody knows this, that when Einstein constructed general relativity, it was constructed so as to reduce to Newtonian gravity in the weak what was then considered the weak field limit. Now that is a assumption, right? If we had, in fact, people I was watching a video by Philip Mannheim the other day. He has been promoting conformal gravity for a long time, and he made this point that actually, if we had found quantum field theory before, general relativity, then the story may have been different. Might not have taken the limit that Einstein did, because there are two separate logical parts to his program, right? And they don't necessarily have to be tied together. So you could, in fact, consider different dynamics for extremely low accelerations, without sort of violating the equivalence principle. But look, I think that should be a discussion for another day, because you have already gone an hour over the allocated time. But Petros Rapidis says,
Unni has a comment here.
yeah, so I should say that Petros Ravidis is an experimental physicist, particle physicist. He was spokesperson of the neutrino detector in Pylos in Greece for a long time. I'm interested to learn that he was never quite convinced by the accelerating universe. There is also, I see, another well-known particle physicist also from Fermilab, Ashutosh Kotwal, online. So I'm glad that at least they are listening into these discussions, because I hope to have at least provided them some degree of, how shall I put it, demystification of the astronomical jargon, which takes a long time to kind of get to. But I'm fairly certain of everything I have said. I would not have said it unless I was quite sure that that is indeed the case.
So,
Right.
Subir, we
Uni
can
has
end
come
with
back to, sorry?
Yeah, please go ahead. Yeah,
Uni
Unni's
has come
remark.
back to ask a question that many people ask, but the total normalized density should be 1 in a spatially flat universe. But by definition, things should add up to 1, yes. But we don't know what are the things that should add up to 1. We know matter, that is one of the components. We know the curvature, that is another of the components. The third component is supposed to be lambda, but there could be a fourth component only, and a fifth component, and a sixth component, if you allow for departures from homogeneity and isotropy, for example, or if you admit of the possibility that the matter filling the universe is non-ideal. These are all possibilities. and they would all contribute additional terms. So that sum rule will not have just three terms. And therefore, when you conclude that omega lambda must be zero point 0.7 because you need to make up one, the real statement is omega lambda plus omega x plus omega y plus omega z, whatever, that should add up to zero point 0.7. And you can't really tell which one of them, if any, is zero point 0.7. Sorry, I hope that was clear, right? I mean, that statement that things should add up to one is simply based on this argument here, this sum rule, which is following in this limited model. Yeah. Yeah, so he agrees that he didn't mean lambda, but whatever it is should add up to one. I agree. It could be curvature, for example, because when we say that curvature is zero, that is the global curvature. Of course, localized, depending on how you're doing the averaging, you could have significant curvature on small scales. You know, if I was sitting next to a black hole, I would see a pretty high curvature. But that is only local. That is not globally the case. Globally, back to the last scattering surface, averaged over all irregularities, the curvature does appear to be close to zero.
Yeah, thank
Okay,
you, Subir.
sorry.
Could you kindly stop sharing your
Yeah.
screen
Okay.
slides so that we
Yeah.
can see everybody? Yeah,
Yeah.
great. So any more comments, anyone? Otherwise, we could wind up.
I, I think you have tired
So that
everyone
was,
out.
there's a great discussion, Subir. Thanks so
Thank you.
much.
Yeah.
I hope we'll hear more about this in the coming years, of coming months. Yeah. So, Michael, are you there?
Okay. Thanks a lot. And I appreciate the comments in the chat. It looks like the diehards who stayed till the end did enjoy it. And
Yeah.
as usual, I'm happy to receive further questions later if necessary. But if you, when you put this thing on YouTube, please cut out the discussion before we started because
Yeah,
that
yeah.
was.
Michael always does that. He
Michael does that.
starts
Yeah,
with
yeah.
a lecture. Yeah.
But do live in the last part where Alvaro
Yeah, yeah, yeah.
indiscreetly
That
said about.
we don't censor anything after the
Exactly.
speaker
Say
starts
say it like
talking.
it is, yeah.
We have
And
never
I was
censored.
also happy to see that some of my cosmologist colleagues like Ed Copeland were online because
Mhm.
I think the thing is that to be quite honest, a very good way to avoid facing unpleasant facts is to bury your head in the sound, so and the sand, I mean. So
Mhm.
I should say a lot of people have decided that they don't want to hear what I've just said in this talk, even though
Mhm.
it is all published in refereed journals, even though I would like to believe that what I'm saying is all verifiable, reproducible, certainly facts, because in
Right,
all the
right.
papers I mentioned, we provide the software and the data with which those
Mhm.
conclusions were arrived at. So, we are
Mhm.
not doing one of these things where later it turns out there was impossible to reproduce the conclusions.
Mhm. Right,
So
I
thanks.
agree.
Let's leave it there, and thank you for
So
hosting me.
much.
Yeah.
Thank you, Subir. Thank you,
Yeah.
everybody. So,
Okay.
just check there were any chats. Yeah, they all thank you chats.
Yeah.
So I will say bye to all of you. We
Okay.
meet now on 3rd September for Andrew's talk.
Yeah.
So I will close the session now. Thank you. Or
Thank
maybe
you.
Subir, you have to close the session because you are the
Oh, I
host.
see. Yeah. So I'll press end and then that'll do it. End meeting.